Hello, this will be a demonstration of proposition 4 from book 4 of Euclid's Elements, which requires us to, in a given triangle, inscribe a circle. We are given then the triangle ABC. So, ABC. And the task at hand is to inscribe a circle into this triangle ABC. We begin by bisecting the two angles ABC and ACB, and they'll meet at some point D. There is a proof that they have to meet at some point, but this is trivially easy. And now from this point D, we will draw the straight lines DE, DF, and DG perpendicular to AB, BC, and CA. So we'll have DE, perpendicular, like that. So right angles there. Of another right angle, like so. And final right angle, like so. Okay. We bisect the angles by proposition 1,9, and then we can create the perpendicular straight lines by 112, because the point D is not on the straight lines AB, BC, or CA. And having made these straight lines perpendicular, it's obviously the case that all the angles at E, F, and G are right angles. Now we know that the angle ABD is equal to the angle CBD. ABD is equal to CBD because we bisected the angle ABC with the straight line BD. We also know that the angles BED and BFD, both being right angles, we know that they're equal by postulate 4. Right, so the angle BED and BFD are equal to each other. And we have a common side BD. So these two triangles BED and BFD having two angles equal to two angles, and the sides subtending the equal angles equal as well. We know by proposition 126 that these triangles will be equal in all respects, namely that DF be equal to DE. Now we can prove in a similar manner that DF and DG are equal. So you know that the angle BCD is equal to the angle ACD, like so. We know that these angles here, DFC and DGC, are equal because they're right angles, that's postulate 4. And we have the common side CD, so these two triangles CDF and CDG are equal in all respects by proposition 126, which means that DF is equal to DG. And we had shown previously that DF is equal to DE, and so by common notion 1, we can say that DE and DG are equal. Which means that from this point D, we have three equal straight lines coming from it. We have DE, DF, and DG, which are all equal, coming from this one point D. And so the circle which we describe with the center D and the distance DE will pass through the points F and G. This is a sort of proposition 3,9, where if we have in a circle more than two equal straight lines meeting at a point, then that point's the center of the circle. We have a sort of variation of that, where if from a point we have three equal straight lines coming from it, we know that the circle with this center and with the distance of one of the straight lines will pass through the other points. And so we'll describe this circle with the center D and the distance DE or DF or DG because they're all equal. Right? We do that by postulate 3, obviously. And now, the final step, we have to prove that this circle is in fact inscribed in the triangle. We can do this quite easily. The angles here at E, F, and G being right angles, right, we made them that way in the first step. They are thus perpendicular to radii of the circles at the circumference, at their extremities. So the radii here, DE for example, is perpendicular to AB at the point E, which is an extremity of DE, and similarly DF is perpendicular to BC at the point F, its extremity, and the straight line CA is perpendicular to DG at the point G, which is one of its extremities. And we know by the porism of proposition 316 that the straight line, which is perpendicular to the radius of a circle from its extremity, will be touching the circle. And so the straight lines AB, BC, and CA all touch the circle EFG, which means by definition 4.5, this circle EFG has been inscribed into the triangle ABC. Now, this being what we set out to do, we are done with the proposition. Into the given triangle ABC, we have inscribed a circle EFG, QEF. Nothing to add to this proposition, so I'll simply move on to 4.5.